I've got this list of numbers, and I'd like to do something to each of these numbers. So what do I want to do with each of these numbers? Well, let's do something simple to start. We'll just double each number in the list. How should we handle this? We could manually handle it. In other words, we could write our own completely homegrown solution, or we could look for a library function to help us out. Now, the right answer to this type of question is almost always use the library. It's way easier, and you end up with less code to write and test and maintain, but sometimes it's hard to appreciate the benefits of using a library if you haven't done it the hard way first. So we'll start off by solving this the hard way first, then we'll contrast the manual way, the hard way, with using a library. I'm going to write a module named util, which will contain our new functions to double the numbers in our list. I'll start by creating a function named double, which will take a list, and I'll add a guard on this function to check that, in fact, the argument is a list. Next, I'll create a helper function named doDouble, passing in the list. This doDouble function obviously doesn't exist, so let's create it. Now keep in mind, we're going to use recursion to work through our list of numbers, which means we need to handle a couple of cases. We need to handle the base case, which handles when the recursive solution should end and just return a value. And secondly, we need to handle the recursive case, which is when the function should call itself again to continue to solve the problem. I'll handle the base case first. So what is the base case in our situation? Well, when the list that's passed into doDouble is empty, in other words, we've handled each element of the list, well, that's when we're done. So an empty list represents the base case. Now remember, our recursive solution should ideally be set up for automatic tail call optimization, which means everything needs to get passed from one recursive step to the next via parameters. So there must be another parameter for this function, which contains our doubled numbers. I'll name it newList. So what should our base case function do? Well, it should just return our solution, which is passed into it as the newList parameter. Now, if you're new to recursion, and your only exposure is from the last couple of videos, well, what I'm doing here might seem a bit fuzzy, but hang tight for a moment. This function will make more sense when you see the next function clause we write that handles the recursive case. Okay, the next function clause for doDouble will match on a list, and it'll destructure the head from the tail. Then it'll also get past the new list we're constructing. In the body of this function clause, I'll simply call doDouble, passing the tail as the new reduced list. And for the second parameter, I'll return a list which has a new head value of head times 2, which is perpended to the new list. There's a small issue with our doDouble function, which is the fact that up here in the double function, we're only calling doDouble with a single parameter, the list of numbers to act on, but doDouble needs two parameters. At least that's how it's currently written. We could just add an empty list here, or we could add another function clause that defaults the new list to an empty list. Well, actually, we're not going to write an entire function clause. We'll just write the head of a function. Okay, well, there's a few issues with our solution, but there's one big glaring issue, which you'll see if we try and call our double function. So let's do that. I'll create a new variable named doubled, and I'll bind it to the value returned by calling our new util module's double function, and I'll pass in our list of numbers. Now I'll go ahead and run the script, and as you can see, our numbers were doubled, but they were also reversed, which isn't what we wanted. Okay, so what should we do? Well, let's just reverse our list in our base case function. So in our base case, I'll call reverse, passing in our new list. Will this code work as written? Well, no, because the way we're calling reverse suggests that reverse is a function in this module, and of course, there is no reverse function in this module. So we're back to the question, should we write a reverse function, or is there a reverse function we can use in the standard library? You can probably guess the answer to this question. there is a reverse function we can use. Again, writing a reverse function wouldn't be too tough. It's essentially what we did in do double without the multiplication by 2, but let me show you how you can use the reverse function that's in the enum module. You've seen how you can call functions using the fully qualified module and function name, such as enum.reverse, but there's another option you can use, which I'll show you right now. There's a macro named import that we briefly used in an earlier video. You can use the import macro to import another module's functions and macros into the current module. So for example, if we wanted to use this reverse function, as you see it here, we could simply import every function and macro from the enum module into the current module. Doing this allows you to call all the functions in the enum module without needing to type enum.functionname. Instead, you can just call the function like we're doing here. But here's the thing. Often, it doesn't make sense to import every single function and macro because you're polluting the current namespace with lots of functions that you have no intention on using, and you could end up with name collisions, where your module has a function with the same name as the imported module, which can lead to ambiguity. So another option is to import only the functions you intend on using, which is done by adding a keyword list to the end of the import macro, which includes the only keyword that's set to a list of functions you want imported. The way you specify the function to import is by referencing the function name using an atom, but just specifying the name of a function isn't quite enough information. All functions in Elixir are identified by name and arity, so to import a specific function, we've got to say which function we want imported by its name and its arity in a keyword list. Okay, now that we've imported the reverse function and used it in the base case of our do double function, let's try it out. And as you can see, it worked. Cool. You know, these double and do double functions are very specific. In other words, they only double a list of numbers. Well, what if we wanted to triple the list of numbers? It seems kind of silly to write a triple function just like the double function, doesn't it? What if we made these functions a bit more generic and reusable? Here's what I mean. There's 3 basic things happening in our do double function. We're using recursion to step through a list, then we're transforming each element of the list by multiplying the element times 2, then we're constructing a new list with the transformed element. Stepping through the list and constructing a new list are pretty generic operations, but the transformation here is pretty specific. So how should we make this specific part of our function more generic? Well, what if our do double function was past the logic it needed to do this data transformation? For example, instead of taking the head times 2, we instead called an anonymous function passing in the head. So where does this function come from? Well, we need to have it passed into our do double function as a parameter, so I'll just add a new parameter for the function here, and of course we'll need to pass the function into every other call to do double, here, 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 and here. Then we'll need to have the function passed into the double function as well. Let's go modify what we're calling the double function, passing in an anonymous function that takes a single parameter and then multiplies the parameter times 2. Do you see what we did here? We made our function much more generic and reusable by allowing the transformation function to get passed into our function. Essentially, we've turned our double function into a higher order function that now gets passed data here and any type of logic here. Now, if we wanted to triple each number in our list, we'd just need to pass in an anonymous function that tripled the value. Okay, it's pretty obvious at this point that the name of our functions, double and do double, don't represent what they currently do. So we should rename them. Any thoughts on what to call them? Well, there's a common term used for what we're doing here, which is map. Now, when I say map, I'm not talking about the map data type. I'm talking about map as an operation. In other words, to go from one thing to another. So I'll rename double and do double to map, and we're done. Okay, we went through this exercise for practice and to introduce a few new concepts along the way, but we really didn't need to create our own map function because there's already a map function in the enum module. So instead of creating and using util.map, we could have just called enum.map and passed in the list and an anonymous function, which is the best option. Now, one more thing on mapping. Our example was a simple example with integers and multiplication, but keep in mind you can map over lists that contain any type of data, and you can transform that data into whatever you think is appropriate. Okay, in the next video, we'll look at another commonly used function from the enum module, the filter function.